Unit 7.1 to 7.3 notes, where we are going to look at creating a solid of revolution. So it's volume by integration. So notes D, and what we're going to be doing is we're going to be talking about volume instead of area. And there are two methods that we are going to use in AB calculus. We are going to use a disk method, and then we're also going to use a washer method. So these notes will only focus on a representative disk. So reading through all of this, a solid of revolution is created when you have a two-dimensional area, like right here. So here's an area, and you take that area and you revolve it about some axis of revolution, whether it is the x-axis or the y-axis or some other horizontal or vertical line. So you can see in this picture here, there are these representative disks. Now those representative disks each have a thickness of delta x. And then if you think about just taking one of those disks out, it's almost like a penny or something. It's not the best drawing here. I'm going to try to draw again. So a representative disk. So if I take one of these representative disks out and I look at it, it looks like a cylinder. So from geometry, if I take that cylinder and I put it so that it's upright, and the volume of a cylinder is area of the base times the height of the solid. Here's the height of the solid, but this is on its side. So this would be its height, but our height this time is delta x. So volume is area of the base. The base is a circle, so that's pi radius squared, times the height of the solid. So in this case, it's dx. So if we look at our calculus formula for the disk method, what I did was I took my geometric formula and I put it into an integrand. So notice I've got pi radius squared dr instead of dx, and everything is in terms of whatever the radius function might be. So r is the function or the distance to the graph. This other formula right here is what most textbooks will use, the horizontal axis of revolution. So it is pi r squared dx. And remember, the dx or the dr or the delta x is the height or thickness of each representative disk. So this is the formula that we're going to be using. So it's just like area, where you would subtract the two functions in order to get the area bounded by the graph of two functions. But now we have a three-dimensional representative figure, which means that we're also going to be using pi because we are doing a rotation. So what I did was, let's say our graph looked like this. Oops, I don't want to erase here. Let's say that our graph right here was the function, and then we're talking about this region right here, and we revolve it about the x-axis. So I kind of drew, it looks almost like a ham, a spiral ham. And so I kind of redrew a three-dimensional figure again. So I'm going to do a couple of these problems, not all of them, and you can check the worked out solutions. So I'm always going to have at the top kind of that formula, volume equals from A to B, and those are the limits in terms of x, pi r squared dr. Or we could also write the pi out front, because it's a constant, A to B, capital R x squared dx. So here's our first example. Set up and evaluate the integral that gives the volume of the solid form by revolving the region about the x-axis. So we'd be taking this region and revolving it. So it would look something like this. And then this would be that representative disk right here. A little hard to draw it three-dimensionally, but we're going to use this formula. And when we're in the classroom, I'm going to show you some animations of what this looks like. So I'm going to write pi. I'm going to come back to A to B. My function, because it's that blue region right here, here's my function in terms of x. So it's 4 minus x squared. Keep in mind that I have to square the function or square the radius. And then dx. Now my limits are going to be in terms of where we start building the discs and where those discs end. So from 0 to 2, 0 to 2. So that is going to give me pi from 0 to 2. Now if I square this binomial, I will get negative 8x squared. Actually, let's put the x to the fourth first. So I'm going to get x to the fourth first. If I expand this, minus 8x squared, and then plus 16. And then from here, this is going to be, I'm going to add 1 and divide by the sum, keeping pi out front, x to the fifth all over 5, minus 8/3 x to the third, plus 16x, and I'm going to evaluate that between 0 and 2. That's the antiderivative. Now if I do the fundamental theorem, I will get down to 32 over 5, plugging into and making it to the fifth power, minus 64 over 3, evaluating at 2, and then plus 32, and then if I plug in 0, the whole second evaluation will be 0. All of this will simplify to 256 all over 15. And I did forget to wedge in the pi in the front here. Pi will always be part of your answers for these volume problems. And this is units to the third power. Okay, so that is part D. Or excuse me, example 1. So we're just squaring the function that is there, including pi, because we have a three-dimensional figure now to approximate that volume. So let's also look at example 2. So we have this picture with this function, which is a radical function. We're going to revolve that region about the x-axis. So here's what it would look like. And your representative disk, remember, has a thickness of delta x, or a height, and then here is your radius. So I'm going to integrate between 0 and 2. I'll put the pi out front. I'm going to square the square root, in this case, dx. So there's my setup. Then when I integrate this, let's say I had to do this without a calculator. When you square a square root, you just release the radicand. So be careful with the algebra. I'm going to add 1 and divide by the sum. Then that is going to be pi, when I plug in 2, of 8 minus 8/3 minus 0. You could leave your answer like that, or this will give me a final answer of pi, and then 16 all over 3. So you will have an answer of 16 thirds pi units to the third for your volume. All right, you can also do a revolution around something other than the x-axis. So if we revolve it about the y-axis, so our figure in this case would look like this, and then your representative disk this time is delta y. So everything has to be in terms of y. So when we revolve about the y-axis and you have a disk, everything is in terms of y. So I'm going to go between 0 and 4. Your limits now build this way. Okay, so 0 to 4, pi. Now my radius is still going to be squared in terms of y, but I have to have my function in terms of y. So I need to take this and I need to rewrite that so that it's in terms of y. So I've got to write x equals. That is going to give me, if I square both sides, I'm going to have y squared equals 16 minus x squared. I'm going to subtract 16. Divide by negative 1. So let's move this whole thing around. I'm going to have 16 minus y squared. And then x is equal to plus or minus square root of 16 minus y squared. So I'm only doing the top half here. So when I set up my integrand, I'm going to keep this in terms of y, but only use the positive part because I'm only talking about the positive portion of the graph. So this is the square root of 16 minus y squared. Then that's going to equal pi out front, 0 to 4, 16 minus y squared, because I'm squaring a square root. Add 1, divide by the sum. And then from here, I am going to, sorry, my phone is ringing. This will be a final answer. I'm just going to give you the final answer. You can evaluate it if you need to. I believe that final answer is 168 all over, 128, not 168, 128 all over 3 pi units cubed. Make sure you watch or look at the rest of the worked out solutions for the other examples.